In the last lecture, we had met this wonderful circuit component, the operational amplifier. We had also seen that it was great as a voltage to voltage amplifier in all parameters. It had a huge input impedance, very low output impedance, and a huge gain. Unfortunately, at least so it seemed at the time, this very fact that it has a huge gain prevented it from working like an amplifier in all the cases we had met in the last lecture. So we had already seen the op-amp in use, but all of those circuits were circuits where the op-amp was used in a non-linear mode. At the end of the last video, we discussed that if we want to use the op-amp in a linear fashion, what we will have to do is we will have to ensure that the input voltage difference is tiny. And the way to achieve that is via negative feedback. So we are going to explore linear op-amp circuits and how to use negative feedback to get the op-amp to behave linearly in this video. So how do you make an op-amp work linearly? As I said, you use negative feedback, and let me show you the simplest way in which negative feedback can be enforced. Just connect the output back to the input via a resistor network. In this case, all we have done is join the output here back to the input using a resistance R2, which is also often written down as the feedback resistance. So you would often see this written as RF and this one as RI. These are just different notations that you will see in textbooks. RI for the input and F for feedback. And let me emphasize once again that although I have not indicated which terminal is negative and which terminal is positive as far as the input terminals go, I am actually using the standard convention that the upper terminal is the inverting terminal. Let me just put in the minus and the plus here for emphasis. For negative feedback, you need to connect the output back to the negative or inverting input, as opposed to the Schmitt trigger circuit which we saw a while ago, where we were actually connecting the output through a R1 R2 network but back to the non-inverting input. That's not negative feedback. This one is. And as you will soon see, analyzing a circuit with negative feedback, assuming that the op-amp works in the linear region, is actually very simple. In fact, most of the calculations you can do in your head or just by writing down a few lines on your copy. But in order to understand this issue better, what we are going to do is we are going to look at the model, effective amplifier model for the op-amp. That is the same effective model that every amplifier has, and try to understand how this behaves in terms of its parameters like the open loop gain and so on. So just to remind you, this is what the op-amp would of course look like. This is the same circuit, but the op-amp essentially looks like there's an input impedance, in this case called ZD, the differential input impedance, connected between the two inputs. It also behaves like a source, voltage source AOVD, where A open loop or A0 VD, where VD is the difference voltage. In this case, for this particular circuit, VD is of course nothing but V minus, because V plus is 0, the non-inverting input being grounded. And you have an output impedance 0. Well, the great thing about an amplifier as op-amp, as we have been saying, is that ZT is huge, ZO is very tiny, and A0 is huge. So later on when we analyze an op-amp circuit, we are just going to make the assumption that A0 is infinite, ZT is infinite, Z0 is 0. And that will make the analysis very simple. But for the time being, just to sort of illustrate what happens and why does having a huge A0 help, let me start with a more realistic picture where A0 is really not infinite but some very large but finite quantity. Let me now try to analyze the circuit in terms of the op-amp parameters A0, ZD and ZO. We will start by writing down the full equation assuming all three parameters are finite and non-zero. But in order to understand the concept of negative feedback and how it really helps, it's actually more useful to focus on the behavior which you get because of the huge value of A0. So first let us write down the equations and then we will simplify them somewhat depending on what we really want to focus upon. So as you can see, this is nothing but the nodal equation at this point. V minus, this node is, which is at voltage V minus, is connected to three other nodes, the ground, Vi and the Vo. And you just add the three admittances, 1 by R1, 1 by R2 and 1 by Zd, and multiply that by V minus. From that you subtract minus Vo by the admittance which connects it to V minus. So minus Vo by R2. Similarly minus Vi by R1. Of course there should also be this voltage V plus, minus V plus by Zd, but V plus is 0. So you just don't have term for that. This is just standard Norton's method or simply KCL applied to this node. If I apply KCL similarly to the next node, that is the one marked here, I will simply get Vo times the admittances 1 by R2 plus 1 by 0 minus A0 Vd into 1 by 0, that's for this part, and minus V minus by R2. And you are done. These are the two equations that you get. Of course, Vd is minus V minus, V plus being 0. So you can solve this equation for V minus in terms of Vo. Take this, plug it back here. Then you can get an equation which involves only Vo and Vi, and you can solve that to get Vo by Vi ratio and figure out what the gain is for this particular circuit. Well, that's correct, but that will give you a rather cumbersome looking expression. But as I said, let us focus primarily on the role which A0 plays here. Remember, A0 is huge, but in order to see its effect, what we need to do is assume that it's finite, which is of course true, but it's very close to being infinite. And what we will do is we will ignore the other two parameters for the time being by setting Zt to its ideal value, which is infinity, and setting Zo, the output impedance, again to its ideal value, that is 0. Now, of course, if you try putting Zd equals infinity, this equation simplifies immediately. You get V minus into 1 by R1 plus R2. This gets popped. The other two terms stay as they were. Well, this equation needs a slightly more careful handling because, of course, you are dividing by Zo here. Substituting Zo equal to 0 will lead to a disaster. But it's easy to see that all you need to do is multiply first by 0 and then put 0 equal to 0. And if you do that, well, this term, well, only this term is going to survive. We're going to get Vo from here, minus AOVD from here, and this term is going to vanish. So you get Vd equals Vo by Ao, which of course is not a surprise because if Zo were really 0, then this point is directly connected to the effective source inside A0 Vd. So Vo will be A0 Vd. More importantly, Vd will be Vo by A0. Or here we have written in terms of V minus. Of course, V minus is minus Vd. So you get V minus, which is what is going to go in here, is minus Vo by A0. And if you take that into account, this is the equation you're going to get. Now let me just quickly point out that if you use the ideal value for A0, which is A0 is infinitely big, this term drops out and you get a very simple final result. You get Vo is minus Vi into R2 by R1. What that means is this particular amplifier produces an output which is proportional to the input with a negative sign. That means the output is going to go up when the input is going down and vice versa. But with a factor of R2 by R1, which means the gain of this circuit will be minus R2 by R1. The minus sign showing the 180 degree difference in phase between the output and the input. That is, one goes up when the other goes down. But the fraction by which the output gets multiplied is simply R2 by R1. That is of course assuming the ideal situation where AO is infinitely big. But even if AO is not infinitely big, where AO is finite, what you see here is this. The gain comes out to be minus R2 by R1 divided by, this just requires, well, slightly manipulating this particular expression, and you get 1 plus R1 plus R2 by R1 times A0. So of course the final gain of the circuit, this A is the gain of the amplifier. This does depend on the raw gain A0 of the op-amp. But notice one thing, R1 plus R2 by R1 typically would be a number which is more than 1 of course, but is of the order of 1. It's not going to be huge. It can be 10 or 20 or whatever. But you're dividing it by A0, where A0 is really huge, 10,000, 20,000, even more. So what happens is, well, for almost all practical purposes, you can simply ignore this term. What is important is, precisely because A0 is so big, how big it is doesn't matter. That's the beauty of negative feedback. It stabilizes the output of your circuit from vagaries of fluctuation of the circuit parameters. A0 is a huge quantity, but it's also rather fickle. It changes with temperature, it changes with operating voltage, it changes if you were to switch one op-amp from a given family by another, and it changes quite a lot. It doesn't really matter. I don't really care whether A0 is 10,000 or 40,000. This term is going to be negligibly small anyway compared to the 1. So for all practical purposes, we are going to get a gain for the circuit which is minus R2 by R1. And that is a very stable gain. This brings us to a very important concept in the analysis of linear op-amp circuits, that of the virtual ground. Now, we have already seen what this really is. In order that an op-amp behave in the linear region, VD must be, well, if it's in a linear region, it has to be VO by AO, the output voltage divided by the open loop gain. And because the open loop gain is so huge and the output voltage is limited to within plus minus Vsat, this must be nearly 0. And that implies that the two differential inputs of the op-amp must be at almost the same voltage. In fact, the difference between the two voltages in this case is expected to be so small for most op-amps, well, in fact for all op-amps, that you can safely neglect the difference. Now in many applications, the plus input, as in the inverting amplifier, the non-inverting input, the input marked plus, is grounded. So what you can have is often, okay, not always, V plus is 0 because this is actually grounded. And then V minus would be very nearly 0 because it's not actually grounded, but because of this fact that VD is nearly 0. Okay, just remember that this works only as long as the op-amp is working in the linear region. But if it is, then V minus is nearly 0 and that is called virtual ground. There are people who object to this nomenclature. They say virtual ground is not a great name for this, for the simple reason that all this is saying is VD should be nearly 0 in the linear region of the op-amp. That is, the two inputs should be at nearly the same voltage. Of course, if one input is grounded, then the other is virtually grounded. That's fine. But very often, in many applications, one of the inputs is not grounded, as we will soon see plenty of such examples. Then the other one is not really grounded, virtually or otherwise. It's just at a voltage which is very close to the previous input. Now, this has led many people to insist that you should really call this virtual short, because virtual short implies that there is no voltage difference between the two inputs. That is, the two inputs are shorted or virtually shorted. The one problem with that nomenclature, of course, is that if you say that 2 points are shorted, it would tend to imply that any amount of current can flow through that and you will still get a 0 voltage difference. However, op-amps have huge differential input impedances, which means that no current or almost no current flows in between the two inputs. Now that would be sort of contrary to the terminology short. So after all, it's just a terminology, so it doesn't really matter whether you're going to call it virtual ground or virtual short. I'm going to call it virtual ground throughout, knowing fully well that in many applications, one of the inputs is not held at ground, so the other one will not be. So when I say virtual ground, please keep in mind that all I mean is that the two inputs of an op-amp are held at nearly the same voltage. One important caveat here, of course, is that this works only when the op-amp is in the linear region. So let me just go back to our example of the inverting amplifier once again, and just let us try to put in some numbers in the game. So this was our inverting amplifier circuit. Output, and just to keep life simple for myself, I'm going to draw the resistors like rectangles. There of course is a standard convention for drawing resistors. I'm just going to use that because that makes my life a lot easier when I'm drawing it in front of you. Well, my drawing skills are not really much better this way, but still it's better than what any attempt of drawing a zigzag resistor would be like. So this is our inverting amplifier with two resistances, and let me just use two specific values here, 1 kilo ohm and 10 kilo ohms for the two resistors. This of course is called the feedback resistor and this is the input resistor, and here I have built or designed an op-amp circuit whose gain VO by VI should be minus 10, minus R2 by R1 or minus 10 in this case. Let me just stress once again that although this need not be labeled because we are following the standard convention, the upper input is the inverting one and the lower input is the non-inverting one. And because the output is connected back to the upper input, you do have negative feedback. Now let us try to understand what the output will be or what the currents in the circuit will be when you have 0.3 volts as input. Now we have already seen this calculation just a while ago, but let me just point out that you could just as well do this in your head like this. This is actually grounded, so this must be virtually grounded, so it must be at nearly 0 volts. So voltage drop across the 1 kilo ohm is 0.3 milliamperes because that is exactly what you get when you divide 0.3 volts by 1 kilo ohms. All of this current, or nearly all of this current, only nanoampere order current goes into the op-amp. So nearly all of this current goes through this branch up here. So when 0.3 milliamperes is flowing through 10K, you are going to get a 3 volt drop. And that means that this end will end up at minus 3 volts. So that's fine. So we have understood basically how this ends up giving a gain of minus 3 volts. Just to show that there could be a problem with this idea, what if we had an input say of 3 volts? If we follow the same kind of analysis, this end is at 0 volts, actually 0 volts because it's grounded. So this has to be, according to our theory, at approximately 0 volts. So the voltage drop across the 1K resistor now is 3 volts. So I'm drawing all these numbers in purple so that you can distinguish from the green ones up there. The drop across the 1K resistor should be 3 milliamperes. Same argument, the current going through this branch should be 3 milliamperes. So now this 3 milliamperes is flowing through 10 kilo ohms, and if you just follow Ohm's law, you are going to get a drop of 30 volts, which means according to our very simple calculations here, the output to the op-amp for this inverting amplifier circuit should be minus 30 volts. Now, all of you must have realized that there is a big problem here. As I kept on stressing, the output voltage comes from the power supply ultimately. So if you have a 3 volt input and you are predicting a minus 30 volt output, which of course is fully consistent with this VO by VI being minus 10, you run into this problem. You are apparently getting much more output in the negative direction, of course, than your power supply allows you to. And we already know what will happen. We know that the output will not be minus 30 volts. It will be, let's just say, minus 12 volts. It will be minus Vsat, and as I've said, it will be somewhere around minus 11.5 perhaps, but for the sake of conversation, let's just say minus 12 volts. So the question now is exactly what went wrong with our analysis here. Apparently all we used was Ohm's law, and you can definitely not fault Ohm's law. Remember, we use the Ohm's law only for voltages and currents involving resistors, and there you can of course use Ohm's law. It does not matter whether the resistor is connected to an op-amp or something else. So let me quickly point out the flaw which led to this absurd answer that the output should be minus 30 volts. Most of you may have already guessed that, and in fact, for the very fact that the op-amp is actually showing minus 12 volts, minus Vsat, should immediately tell you the answer. The problem is not with the application of Ohm's law. The problem is not with the assumption that almost all the current which is flowing here is flowing here. The problem is simply with the assumption that virtual ground will work. Remember, virtual ground works only when the op-amp is in the linear region, and this is sort of circular, although really it's not, but it may sound circular, that the op-amp will work in the linear region only when you have sufficient amount of negative feedback. You do have negative feedback here. The output here is connected back to the inverting input, but the amount of negative feedback is dictated by the ratio of the two resistors, and in this case the negative feedback simply is not big enough to keep the op-amp in the linear region. So what will happen actually is that this statement will fail. This was, remember, under the assumption that VD is VO by AO, and that's not really correct. It's not the output voltage by the open loop gain, because that formula works only in the linear region. So now, an important question could be, what exactly is the voltage here and how much are the currents flowing through the two resistors? Of course, it can't be 3 milliamperes, because if 3 milliamperes did flow, then you would end up with minus 30 volts. And the answer is now simple. If you look from this point, between this point and the input, and going through the two resistors, you will see that there is a drop from here to here of minus 15 volts. 3 volts on this side, minus 12 volts on the other, so minus 15 volts is the drop. And the total resistance in this path is 11 kilo ohms. And despite the fact that there is a branch here, this still is a series circuit for the simple reason that the op-amp will draw very, very little current. So you can neglect this current and insist that the same current flows through both the 1K and the 10K, virtual ground or not. The same current flows through this and this simply because the op-amp will not allow much current to flow in. So you get minus 15 volts divided by the total resistance 11 kilo ohm, standard simple series division formula, and that times 1K. Okay, 15 volts by 11K is the drop across the entire combination. That times 1K is the drop across the 1K resistor, so 15 by 11 volts. So what is the voltage at this point? It's simply 3 volts minus this. So a bit more smaller than 2 volts. So as you have seen, you have made an assumption of virtual ground when you derive this expression for VO by VI, and that will work as long as the op-amp stays in the linear region. And the quick way to figure out whether that's happening is simply to look at the output voltage. If the output voltage predicted by assuming that the op-amp has maintained virtual ground, the two inputs of the op-amp are at nearly the same voltage, turns out to be within plus minus Vsat, that is the predicted value of Vo turns out to be within plus minus Vsat, then you are in the linear region. So whenever you have an op-amp circuit with a negative feedback in place, you may start out by assuming that the negative feedback is sufficient. You may start out by assuming that there is virtual ground, do your calculations, predict the answer, and if the final value for the output voltage turns out to be outside the plus minus Vsat range, then you go back and say, okay, this assumption of the linear region was wrong. The op-amp output will be stuck at either plus Vsat or minus Vsat depending on whatever sign is being predicted. And using that and giving up this virtual ground assumption, you will be able to analyze the entire circuit. So, as I pointed out, it is a huge open loop gain of the op-amp which makes this possible, makes virtual ground possible. And we have demonstrated once a while ago how to analyze the circuit taking into account the huge gain of the op-amp. But from this point on, we are going to assume that the op-amp is ideal, the huge gain really is infinite, and Vd is really zero. Well, it's not really zero, but it's close enough to zero for all practical purposes. Just to stress once again, the caveat is you're assuming that the op-amp is in the linear region. So let us just use that and try to analyze a few more op-amp circuits quickly. When I say quickly, I mean really quickly. As you will soon see, analyzing op-amp circuits, especially linear op-amp circuits, is very easy because of this virtual ground demand. So the next circuit we are going to analyze is a non-inverting amplifier. If you look at this carefully, it's essentially the same circuit as the inverting amplifier, except that here this end is grounded instead of putting the Vi here, which we did for the inverting amplifier, and the non-inverting input is not grounded. That's where you have to give your input voltage. So now let's quickly analyze what the output of this circuit will be, and I'm going to just do the calculation on the circuit itself. If this is at Vi and we have virtual ground, this will be almost Vi. Let us note that I am saying almost simply because I want to be very precise. I could have just said it is Vi. You would hardly be able to tell the difference. Now, if this is at Vi, how much is the current through R1? It is easy. You have Vi on this end of the resistor, 0 on the other end, so there is a voltage drop of Vi across the resistor. The current will flow towards the left end in the circuit, in the diagram, and its value is simply going to be Vi by R1. So how much is the current here? Well, since nothing gets branched into the op-amp, it is Vi by R1. So how much is the voltage drop across R2? It's simply Vi by R1 times R2. But notice that the current is flowing in this direction, which means this end is higher up than this end. So the output voltage Vo will be plus this, but not this alone. Remember, what I have calculated here is the voltage drop across the resistor. The left end of the resistor is already at Vi, so the right end, which is connected to the output voltage, must be at Vi plus Vi by R1 into R2. So this must be 1 plus R2 by R1 into Vi. As simple as that. So how much is the voltage gain here? For this particular circuit, it's 1 plus R2 by R1. Notice that this expression, of course, is completely independent of the op-amp open loop gain, which by virtue of being so huge has dropped out of our expressions completely. Of course, it did play a role. The role it played was here in insisting that this voltage Vi is the same as this voltage. The voltage up here is the same as whatever voltage you input. Let me point out, this is obviously one place where the name virtual ground is not such a great name, because This end is not actually grounded, the other end is not virtually grounded. But as I said, we will use the term virtual ground to mean that the two inputs are at the same voltage, not that one of them has to be at 0 volts. And the standard caveats of course still apply. This final result will work only when the output is in the linear region. Now, let me point out two more things comparing the inverting and the non-inverting amplifier. We have seen for the inverting just a while ago, the inverting had a gain of minus R2 by R1. This one has a gain of 1 plus R2 by R1. So a gain which is not only positive, it's larger in size. So if you are looking just for getting a large output, you might very well say that this is something you prefer. Frankly, large output can hardly be much of a concern here, because you know that the highest output voltage you can get at all is plus Vsat or minus Vsat. If anything, the extra 1 in the formula for AV just tells you that the circuit will saturate for an even smaller range of inputs. If the gain is higher, you can only make the input so high before you are going to go into saturation. But that is really not the reason why people would say the inverting amplifier is preferred over the non-inverting amplifier. Just to point out one very important thing, I have already stressed this. The real use of the op-amp is in order to do mathematical calculations. Not getting an amplifier which is necessarily going to give you a big output. There is one major difference between the expression R2 by R1 and 1 plus R2 by R1. This gain has to be bigger than 1 no matter what resistors you use. So the non-inverting amplifier cannot give you a gain smaller than 1. But in a mathematical calculation, you may very well need a multiplying factor which is less than 1. The inverting amplifier gives you any size you want just by choosing the resistances properly. Which is one reason why the inverting amplifier is preferred in many op-amp circuits over the non-inverting amplifier, simply because it gives you a huge flexibility. And there's another flexibility here as well. We might say that the inverting amplifier always gives you a negative gain. So what if you want a positive multiplying factor? The answer to that is two negatives make a positive. So if you want a positive gain, you can couple two inverting amplifiers together. Whereas you will never be able to couple non-inverting amplifiers together to get a negative gain. So that way also, purely from the point of view of getting different mathematical formulae in place using circuits, the inverting amplifier should be preferred. Another point, and this one is a demerit for the inverting amplifier, and that involves the input impedance to the amplifier. Not the input impedance to the op-amp, but to the amplifier. Of course, the input impedance of the amplifier is simply how much is the input voltage divided by how much current is drawn by the amplifier. Notice that in this example, how much current is drawn by the amplifier is almost 0, because this input is directly feeding into the op-amp itself, and the huge gain of the op-amp. In fact, huge differential impedance of the op-amp coupled with the fact that the huge gain forces the two inputs to be at nearly the same voltage ensures that very tiny current flows in, which means this circuit has a huge input impedance. The non-inverting amplifier. On the other hand, for the inverting amplifier, you gave your input here. If you gave a Vi here, grounded this, remember if you grounded this end would be grounded virtually. So the current drawn would have been Vi by R1, because the drop would have been Vi across the resistor from here to here, from left to right. That would mean the current would flow from left to right, and the current would have been Vi by R1. So an input connected to the inverting amplifier simply gives you an output current of Vi by R1, which means that the input impedance of the inverting amplifier is R1. It's limited by the input resistor. So the input resistor is the input impedance here. Not for the op-amp, but for this circuit. So As we have been saying, that the input impedance should be high for a voltage to voltage amplifier, and even for op-amp circuits where we are not aiming for huge gains, that's still a great thing to have, simply because that would actually make the output really equal to minus R2 by R1 into Vi without having to depend on how much source resistance your input voltage actually has. So one demerit in terms of the inverting amplifier is that the inverting amplifiers input impedance is not infinite, not the op-amp's input impedance, but only R1. And if you want a big gain, for whatever reason, R1 cannot be very big because R1 is the denominator of this expression. So that's one trouble which you have, especially when you connect one inverting amplifier to another to maybe get a larger gain or to get a positive gain. You have to worry about this. The impedance of the low input impedance of the inverting amplifier circuit essentially means that you are drawing a lot of current from the previous stage, and that may actually cause a large drop before the input is reached, and that may severely impact upon the performance of this system. Since coupling many amplifier stages together to get to a desired mathematical expression finally is often done in op-amp circuits, this may become a bit of a problem. However, there is a solution to this problem which the op-amp itself provides, and that is called the unity gain buffer. If you look at this circuit, it's one of the simplest possible circuits you can have. It doesn't even have resistors. All you have is a wire which is connecting the output back to the inverting input. I hope by now you have got used to the fact that if the terminals are not labeled, the upper one is inverting. So what happens here? You have provided negative feedback. The output is fed back to the input. So, assuming that the system will be in the linear region, you're going to get virtual ground. So, if you have Vi here, once again you see that the nomenclature virtual ground is not perfect. If you have Vi here, you have not 0 here, but almost Vi. But since this is connected to the output by a wire, the output VO will be equal to Vi. That is where the name unity gain comes from. But what is so useful about this circuit, then all it gives you is the output which is the same as the input. The utility is in the buffer part of the name. If you put this between two other amplifying stages, what happens is this circuit will draw almost no current from the previous stage, simply because here the Vi is feeding directly into the op-amp. Nanoampere range currents are going to flow, so almost no currents for all practical purposes. And we are going to get this output here, which is going to be of very low output impedance for the simple reason that the op-amp itself has very low output impedance. So what this circuit is good for is, suppose you have two amplifiers, one whose output impedance, the first one's output impedance were say large, and the next one's input impedance were low. If you have to connect them together, the trouble is the large output impedance of the first op-amp or first amplifier connected with the small input impedance of the second one would actually cause a huge drop in the output of the first one before it was fed to the second. As a result, the overall gain of the circuit will suffer. Both because you're going to end up getting a smaller gain, but more importantly, you will end up getting a gain which depended on many other complicating factors like exactly how big the impedances are. Putting a unity gain buffer between two such stages means you can safely couple them. This is going to almost draw no current from the previous stage, which means whatever output the previous stage gives comes to this one, and this produces an output at very low output impedance to the next stage, which means doesn't matter what the next stage's input impedance is, you are going to simply get Vi fed to the input of the second stage, and the circuits are going to work without any further complications. Now, just to quickly run through a few more circuits, the adder Well, here we have essentially something which looks like the inverting amplifier, but instead of using one resistance R1 here, we are using three resistors RA, RB, RC, and we're connecting this to three inputs VA, VB, VC. Well, analyzing this circuit is child's play once again. This is at 0 volts. So this is almost at 0 volts, virtual ground. The voltage drop across the three resistors are VA, VB and VC respectively. So the currents through them are going to be VA by RA, VB by RB and VC by RC. So the net current flowing into the inverting terminal, into this connection here, not into the inverting terminal of the op-amp, but into this connection, is VA by RA plus VB by RB plus VC by RC. So sigma Vx by Rx, where X stands for ABC here, is flowing into the resistance R2 for the simple reason that very little will flow into the op-amp. So drop across R2 will be this current into R2. So the output voltage, which remember is lower because the current is flowing this way than this end, is going to be minus R2 by VA by RA plus VB by RB plus VC by RC. So this produces a linear combination. In particular, if RA equals RB equals RC, all these resistances were equal and equal to R1, V output will be minus R2 by R1, a gain factor, times VA plus VB plus VC. So as you can see here, the output is going to be proportional to the sum of the inputs, which is why it's called the adder. You can of course choose R2 by R1 accordingly. It's of course an inverting adder. The output is proportional to the negative of the sum of the inputs. As you can see, you can make something more versatile with this by choosing different values of RA, RB, RC. You can get different linear combinations. All you have to do is cleverly choose R2 by RA, R2 by RB and R2 by RC. The only catch of course is here all these coefficients have to be positive. Negative coefficients cannot be achieved by this circuit. And once again the caveat of staying within the linear region, etc. that holds. And of course you could add more resistors to this side instead of stopping at 3 and more inputs. So you may be able to sum up more and more input voltages this way. Okay, but this of course only manages to give you positive linear combinations with an overall minus sign, but they will all come with the same relative sign, that is R2 by RA, R2 by RB, R2 by RC are all bound to be positive. So how do you get a subtractor, something which gives you an output proportional to the difference of two inputs? One simple subtractor circuit is going to come up next. We are going to later see that what you really want is an instrumentation differential amplifier, a more complicated circuit if you really wanted high precision work. We are going to discuss that in the next video. Today I am just going to quickly go through some simple circuits. So subtractor, the simple subtractor is simply made this way. So you have two inputs V2 and V1 and you have 4 resistors, and all 4 resistors, for the sake of simplicity, we have taken them to be equal. So let's now quickly analyze this circuit once again. Now this end is at V1. It's connected to 2 resistors of equal value, and remember the op-amp draws very little current, so this input here, this point here is simply at V1 by 2. Why V1 by 2? Because that's exactly what you get when you divide V1 between 2 equal resistors. Once again we are using the series potential division formula simply because the op-amp draws no current. But if this is at V1 by 2, actually this is virtually at V1 by 2. So this is VD is tiny. So how much is going to be this current? That of course will depend on the relative values of V2 and V1. It's actually going to be V2 minus V1 by 2, the voltage drop across this resistor, divided by R in this direction. And I'm pretty sure you have all noticed this so far. I'm saying it's in this direction, but for that I'm assuming that V2 minus V1 by 2 is positive. If V2 had been less than V1 by 2, the current would actually have been to the left. But still V2 minus V1 by 2 divided by R in this direction. And you know the drill by now. The current through this resistor is the same. So since this resistor also has a value of R, you have to multiply the current V2 minus V1 by 2 by R times R to get the drop across this. So the output voltage VO is going to be the voltage at the left end V1 by 2 minus the drop, and that's simply going to come out to be V1 minus V2. So that's where the name subtractor comes from. The output comes out to be equal to the difference between the two inputs. In fact, it happens to be exactly V1, this input, minus V2. Now, you must have also realized that we could have made it more complicated by simply choosing 4 different resistors here. And that will give you a slightly more general version of this expression. Let that be a homework. Once again, it's a homework which you can almost do in your head or just by writing down a few voltages on the circuit diagram itself. Okay, so what other circuits can we talk about? Let's quickly talk about a few other very interesting circuits. In the next video, we will talk about some more advanced circuits using linear op-amps or using the op-amp in the linear mode, as well as combinations of these circuits to produce really wonderful effects. But today, as we are going to look at simple circuits and quickly analyze them. This circuit, well, what it does should be obvious from what is the title here is called the differentiator, and let's figure out how this works. Notice that this end is grounded. Once again, that means this end is virtually grounded. That means the voltage drop across the capacitor is Vi. The charge in the capacitor is of course CVI, capacitance times the voltage, and the current which flows through the capacitor is simply ddt of that. So that's the current which is flowing this way. So how much current flows through this feedback resistor R? The same. And what is the output drop? R times that. What is the output voltage? Simply negative of the drop, simply because this end is at 0. So the output voltage is going to be less by the drop. So as you can see, the output here is proportional to not the input voltage, but the derivative of the input voltage. So you can do calculus with op-amps. In fact, we will see in the next video some wonderful pieces of calculus that you can do with op-amp. Okay, if the differentiator is there, can the integrator be far behind? No, it can't. Here, well, you are used to it by now. This is at 0. So this is almost at 0. The current through the resistance has to be Vi by R. That current has to flow into the op-amp. So the voltage drop across the op-amp is simply going to be proportional 1 by C times the charge which is stored into it. The charge stored into the capacitor is simply the current flowing through it as a function of time integrated from whatever initial time. Let's say you started the circuit at time 0 to time t. This of course is the charge across the capacitor provided the initial charge were 0. If there were an initial charge, you would have to put an initial potential here. But this is a drop across the capacitor. So VO is going to be minus this. So minus 1 by RC integral VI t prime dt prime from 0 to t. Again, if there were an initial voltage drop across the capacitor, that would have to figure into this. But modulo that, what you have is a circuit whose output is going to be proportional to the integral of the input. Now, to be frank, this circuit has some problems. We are going to explain what the problems are and what the solution to that problem is in the next video. But going along with this line of simple circuits, let us quickly take a look at these two circuits. Well, here we have a diode in the circuit. So, the current here is going to be, well, this is 0, this is almost 0. The current here is going to be ID at Vi, whatever the diode voltage is. And that current flows through this. So, ID Vi flows through this. So, VO is simply going to be minus R times the diode current at the input voltage. So, one immediate application of this circuit would be that if you wanted to draw the diode characteristic curve, you would connect the diode here, change the input voltage, let's say linearly, and for each input voltage just note the output voltage. That will give you a perfectly good I versus V graph, or I versus V functional dependence with this extra factor of R just thrown in. So, one thing is, if you use a CRO and fed it a sawtooth voltage along the X component at the input and connected the output and the input both to the XY mode of the CRO. If you don't know what that means, we will explain that later in a lab class. But if you did that, the CRO will immediately show you the characteristic curve of the diode. By the way, you should realize that this works for any two-pole device, not just the diode. So, you want the characteristic curve for any two-terminal device, you can connect it there. As long as the output stays within the saturation limits, this is going to give you a nice VO versus VI, current versus voltage relation for that particular device. But let me just remind you that ID for a diode was Is e to the power QV by KT minus 1, and in the forward bias case, this factor is typically much larger than 1. So, you get Is e to the power QV by KT. So, the output voltage VO here is going to be minus RIS e to the power QVI by KT. So, you can immediately think of many important applications of this. One important application would be simply that this will work like an exponentiator. You take the input voltage, the output is proportional to the exponential of the input voltage. That's one great thing about this circuit. The other great thing about this circuit is, well, if you change the temperature a bit, this is going to change quite a lot. So, VO is going to change quite a lot, and that might be very useful in controlling temperature with a huge amount of accuracy. Let us quickly go through the final circuit on my board here, which is the one on the right. All you have done is switch the resistance on the diode, and you might have guessed, if this is producing an exponential dependence, this should actually produce a logarithmic dependence. Well, quickly, this is 0, this is almost 0. So, this is Vi by R, same current going here. And when the current through a diode is Vi by R, the voltage across a diode, which is minus VO, remember the voltage drop being 0 minus VO, is simply going to be e to the power minus QVO by KT. I'm ignoring the minus 1. So, VO here depends on the log of Vi. You can fill up the details yourself. But basically what you have is these two circuits produces the exponential function and this produces the log. But now that you have a way of producing the log, you have a way of adding and subtracting, you have a way of multiplying by factors, and you also have an exponential. You should realize you raising a voltage to a power, multiplying voltages together, dividing one voltage by another. All these can be achieved by combining these circuits with the adder, subtractor, multiplier, and so on. So, we have seen quite a few very interesting circuits here in this video. They are going to be very useful, especially for implementing mathematical operations. And in the next lecture, we are going to see some more details of these, some ways to overcome some of the problems these circuits may have, some entirely new kinds of circuits you can design using opamps, as well as well, how to combine these things to do mathematical calculations like solving a differential equation. But for that you have to wait till the next video. Bye for now.